Hello everyone, welcome to our on-demand tutorial um, for NEUSREL. So this tutorial is for making the first steps to use the NEUSREL software wisely. The tutorial has 3 steps, and we start with step number 1, which is everything we need to consider prior to do the analysis. So this is especially in regard to the question, what data do we need? How should we set up or pre-think of the model? Let's dive into this first. Then we go right into the setting. We look at the NEUSREL setting Excel sheet and learn how to set the project up. Then we start a sample calculation, and we will look into the results and learn how to interpret them. And then there will be an advanced part later on where we look into advanced settings of the NEUSREL software. So let's start with step number 1, prior to the analysis. This part is very important because NEUSREL allows us to do a causal analysis a little bit different than conventional structure equation modeling are doing it. That's why it's important to think about a few steps, especially the question, how do we define causality? What are the requirements for assuming causality? And the causality definition we are referring to is an advancement of the basic idea of the Granger causality, which were purely relying on time series data, but you can generalize the idea to the following definition. A factor X is considered to be causal to Y when following assumptions apply. First, X is relevant to explain variance in Y. So it must be important, it must be predictive, it must be useful in prediction to explain Y. This is one requirement. It's not sufficient, but it's a requirement. If something is not relevant to explain Y, it has no direct impact. Second, there must be no third factor outside the model that significantly influences X and Y at the same time. Granger called this the closed world assumption. So basically, you can translate it into two things you should do. Either you can comply to this requirement by controlling every variable, meaning that you control it in an experimental setting, which is nothing else than by controlling, you know that this X has no other influence than your own because you have controlled it, right? So this experimental settings are the means to know that something is independent and there cannot be a third world factor. That's the use of experiments. Often that is not possible to do experiments. If it's not possible, we should strive to include the information which has an impact onto this X and Y. Yeah. Or if we don't know those factors, we might include information that might be indicators for this third factor. And this indicator will be enough to basically control in the model the influence of this third factor. So in short, either you do experiments or you do a holistic model. Typically both is advised if possible. And lastly, the causal directions we have in the model, they should be correct. And there are two ways of make sure that they are correct. The first way is to rely on expert judgment. So there are certain things which are basically known. It is known that the gender of a person does not change no matter whether or not he likes a product, right? So the gender is always the cause or the moderating factor. It's never the outcome. And in this sense, many causal directions can be derived by expert knowledge already. However, there are some causal directions which are not known upfront, and there are mechanisms in statistics that can be used to test for the causal directions. Those tests are never perfect, but it's the best we can do. So these are the three requirements to assuming causality. What does it mean to us? Let's give you more specificity here. So I would like to stretch to you the importance to build a holistic model. And this is so important not only because it is required to make your insights causal, it is also interesting because NEUSREL allows you to make holistic models because it has no requirements on the distribution of your variables. You can include binary variables as well as ordinary or metric variables. So we have the opportunity to build holistic models. Here an example of the so-called confounding problem. If you see here on the left, this is a duration students need to finish their studies. And on the y-axis, you see the income they gain after entering business life. And these are true findings. The findings revealed that duration correlates highly with income. The higher and the longer students need to study, the higher the income. Actually, this is not very plausible. Typically, people assume the opposite, because if you are smart, your duration time is smaller. Because you are smart, your income will be higher. However, it's a fact, it correlates. But it correlates not for causality, it correlates because there is a missing third variable, which is not in the model if you simply look at the correlations. In fact, the two bubbles which you see here, they are different programs. The lower left bubble is business administration students, and the right upper bubble are science students, chemical and physical science students who typically do a PhD afterwards. And that's why the duration time is longer and the income is also higher. So among one program, indeed, the causal relationship is negative. The longer the duration, the income is decreased, right? So once we know the third factor, once we include this factor in the model, it will reveal the right causal direction. You see the causal diagram on the right, the path diagram. Program has a positive impact onto duration and income, and duration itself has a negative direct income. This negative income can only be revealed by including the program into the causal model. This is why we strive to build holistic models, not partial models. I'm stretching this point so much because when I look at scientific papers, they typically do small partial models. It has a reason, but this reason is not always justifiable. The reason is, for instance, that models are built with the mindset of being not explorative but confirmative. So they collect some hypothesis and like to test it. And because there are also not so many hypotheses, models get small. But I think this approach is not useful to gain insights out of data. And it is not needed. And the NEUSREL software enables us to take a different approach. So what is the process with the NEUSREL? So you start with a fully connected dot matrix. Dot matrix means you start with connecting every variable with any others, right? Everything is connected with any others. Then you may eliminate directions which you are confident that are not true, based on prior knowledge. And of course, if you like and if you are confident, you can eliminate even more passes if you are knowing that or want to know that. Because including prior knowledge, including assumptions is a good thing if they are true. It's a bad thing when they are wrong. And that's why we should only use those assumptions and prior knowledge which we are confident about, because we cannot really understand whether this knowledge is true or not. And then finally, we can run the NEUSREL software, and NEUSREL can help us to identify whether or not those remaining passes are valid and what kind of functional relationship can be derived out of the data. So let me summarize the prior analysis. There are 3 points to remember. First, we need to strive to build holistic models. Always start with a blank paper. So write down the outcomes, which drivers you like to understand. Ask yourself what causes those outcomes. Write down a long list and then figure out for which of those potential causes you can acquire data. I'm writing that because typically researchers go the other way around. They look at their data and think, oh, what kind of model can I do with it? That's not the right approach. And typically there are even more data available in the data set, or can be more data attached to it without having another collection process. So that's why it's important to start with the content and with the matter at hand, not with data. Second, use an inverse hypothesis. So conventional procedure is to use only paths for which you have solid hypothesis. This is a confirmatory approach that is not useful in a real world, which has imperfect sets of hypotheses. Rather, collect hypotheses on which paths can be justified to be not in the model. Because knowledge about what's not true is typically more valid than knowledge about what is true. Third, causal direction. Inverse hypothesis on what's not in is particularly for the predefining the causal direction of a path. Yeah, so that's the most important use of your prior knowledge, to define the causal direction of a path, which in most cases can be done. Causal direction can theoretically be derived from data. However, this comes with quite a bit of uncertainty and failure. Valid prior knowledge on this helps building good models. So we have a testing, or even more testing mechanisms with the NEUSREL. However, they are used in a kind of a pre-analysis stage. And you can use that to test the remaining paths where you pretty much unsure about the causal directions. So that's what you need to do before doing any analysis, before looking into the data. Okay, and then we can start setting up a universal structure modeling. How it is done. So setting up a NEUSREL model is very easy. It is done by filling out this Excel sheet. So this Excel template has 4 sheets, and basically it goes as follows. First, you copy in your data. This is data, and in the white cells you see our data. In every row there is one case, right? In this case it is survey data, and one respondent is in one row. In one column is a variable. So line 1 it is simple enumeration of the variables in the model, and line 2 are the names of the variables. NEUSREL does not need those names. It's just for your your orientation. Actually, the model itself is defined in the project sheet. So basically, what you need to do is you give your project a name. Let's call it, okay, it's a customer loyalty model. So don't use blanks in here. You need this name because any pictures which will be generated will have this name on it, so that you can clearly identify which picture saved really belongs to this particular setting. And then in column A, you line up all variables, and the variable can be simply the same as in the data, or it could be a latent variable. So in this case, in this example, these are nearly all latent variables, which means we here define in the green cells which manifest variables belong to this latent variable. The quality, the variables 1 to 7 belongs. So 1 to 7 are quality variables. Expectation is simple V8. It means 8 to 8 value is 9 to 10. Satisfaction is 11 to 13. Loyalty is 14 to 15. And complaints is the 16. We have here the option to invert the variable. Sometimes the scale in market research is reverse, meaning 1 is high and 5 is low. So you can reverse this here, but we don't need to do this in this case. Then we can define missing values. If values are simply missing, if they are simply missing, they cannot be blank here. So this matrix must be filled with data, with numbers, only numbers, nothing else in numbers. Sometimes numbers turn out to be text, they must be converted to numbers. And if your cell is blank, or it should be coded as a missing variable because it is missing, it means that we don't know, then we put here a code for missing. And because I tell NEUSREL that, it will be replaced by something else. Per definition or per default, NEUSREL uses the 20 nearest neighbor methodology. It looks at the 20 nearest neighbor of this case, any particular case, and it computes the mean out of this 20 neighbors. So, and I can here define what kind of measurement model. So how should be quality computed out of this 7 items? There are different methodologies. The easiest and most common one is the linear reflective model. Linear reflective means linear, and quality causes the indicator variables and not the other way around. So now we have defined the variables in the model. We should define now how the starting metrics, which means basically which causal relationships do we allow. So in the rows, we copy the same variables as they are in the rows, and basically the rows are always the cause and the column is the effect. Yeah, as so as I'm described, we can start with a fully connected model. Okay, everything calls everything. Obviously, this doesn't make sense. Quality calls quality, so the diagonal can be 0. To make it more easy to digest, I recommend to kind of use a marker, so a conditional. So now you see exactly which passes are allowed. So we can go backwards. Loyalty, we know loyalty is influenced by everything. Complaints is not influenced by loyalty, but the other way around, as we know from prior knowledge. Satisfaction drives loyalty, not loyalty satisfaction. Value drives satisfaction and loyalty, not the other way around. Expectation is driving the outcomes, not the outcomes expectation. And indeed, expectation drives quality assessment, and not quality assessment drives expectation. So this is the typical model which you may also find in science. Of course, this is kind of restricted now. You could do it other way around, but for simplicity on this test, we just start with this model. So the model is ready now, and the only thing we need to do is to look at the settings, whether or not the settings are good enough for us to go. So there are two tabs here. First, the settings can be seen in options. You see a lot of settings. However, those settings you should care about at the start should be only those in the white fields. Anything else is for the advanced tutorial course. So you really, to start, you really only need the white cells here. Let me go through them and explain to you what it's about. First, size of community of networks. So NEUSREL builds Bayesian neural networks for estimating the relationship between factors and outcomes for any influenced impacted variable. And Bayesian neural networks are known to never get the same, to never come up with the exact same model. And they have a huge number of different solutions which typically gain similar outcomes. So that's, and it is not really, must not be seen as a disadvantage of neural networks. Instead, it is a different optimization method which illustrates that we do statistical inference at uncertainty. Because there's uncertainty, there is a likelihood for many different models, right? So, and we can kind of sample this likelihood by running several neural networks. They typically have similar outcomes, but might be a little bit different in some aspects. And the more networks we compute, the more generalizable our model will be. So typically, you like to increase the size of commutative network if you have not so much data. Not so much data is always referred to the relationship between the number of independent variables towards outcomes. So in this case, for instance, we have in the worst case 5 variables, so 5 factors which drive an outcome, at 150 cases. So the ratio is 1 to 50, which is a good ratio. Yeah, and so that's why we could even go with 5 or even 1 common leaf network. But calculation time is not so long. We can afford to have 10 here. The more the better, basically. Okay, then there is the iteration. Iteration means the following. So this is a structure model. Yeah. So there are latent variables, LV1, LV2, LV3, defined by manifest variables. This, what you see here, are reflective measurement models. So this measurement models will compute the latent variables, and out of this we define the structural model. Yeah. And this is done in an iterative way, because once we have the values for the latent variables, for instance, latent variable 1 and 2, we can estimate a new values for LV3. If I have this new variables of LV3, I can compute new estimates for the measurement model. Right? The first estimate is purely done by principal component analysis, but the second estimate will retrieve information from the other measurement models to estimate the measurement model 3 here. Yeah, and all this must not be linear, but can be nonlinear as well. So, and in this way, we recommend to do at least 3 iterations. But this is only needed if you have latent variables in here. Latent variables which are influenced by other variables in the structure model. If you don't have those, you don't need iterations. If you only have manifest variables in your model, you don't need any iteration. So basically, you put your 1 if you have just manifest variables in here. Okay, what else? Share of validation data. So you could put, for instance, 20%. So 20% of the data would be held out, and we would compute an R² prediction performance on those those validation data. You can do that. There is then the option for bootstrapping. So typically you like to know what's the significance of certain relations. And significance are gained and computed with the bootstrapping methodology. Bootstrapping, in a nutshell, is that we draw from this 250 cases, we draw by random and putting back. We draw 250 cases. Yeah, we draw them and put them back. In this case, we gain a new data set which has some cases double and some are missing. And we do it for 10 or 100 or 200 different draws out of the data set. So the estimation of the model will be then different for those bootstrapping samples, and the variation of the results will give us a statistic which gives us an information how significant certain key KPIs are. You should know that, of course, for every of those 200 bootstrapping samples, a new model must be run. So this will 200-fold the computation time. Because of this, you never start with bootstrapping. You always leave out bootstrapping in order to do a first test run. Once you have done the test run, you are quite confident that every setting is perfectly as you needed it. Then you can put in bootstrapping number for your final calculation. Okay, and then we have in the green part some settings where we can control what will be generated, for which relationships are NEUSREL generates an visualization. Yeah? So what you see here is a threshold for plotting an interaction, a 3D plot, and the threshold for plotting a path function. So basically nonlinearity, for instance. And the value is basically the OEID, which is the NEUSREL KPI for effect strengths. OEID means basically what is the R square which I will lose when I would not have this variable, when I would not have the variation in a certain factor, which explanation power would I lose? This is OEID. And so OEID measures how important something is. It doesn't measure what the impact is, positive, negative, whatever. It simply is, says what's the importance. And you could put here a 0, which will give you for every of those passes a plot. So in here we have now 15 passes in here. So if we do 0, we get 15. For interactions, it's more complicated because these are two-way interactions, and we have here we have 5 by 5, so 25, 3 by 3, 9, 4 by 4, 16, so around 40 or 40 different interactions, so 40 plots. This is handleable. However, if you have larger models, it could be thousands and thousands of plots, where 95% are do not have any meaning or give no information. So that's why it's very important to think wisely about what the threshold is, that you can really handle the results. So let's put point 1 and 0.02. So don't worry, this is a comma because this is a German setting here. Okay, and finally, put here 1 if NEUSREL should compute total effects. Total effect of, for instance, quality on loyalty is the direct effect plus the indirect effect loyalty has over influencing value and value influencing loyalty, or quality influencing satisfaction, satisfaction influences loyalty again. So there are multiple indirect effects, and everything is computed together to gain a total impact figure. And this computation is very complex if you have large models. And NEUSREL does it automatically for you. So now you are ready to go. In the tab Modules are more modules and more features of the NEUSREL software which you might use. However, this is for advanced users, and I will explain this later. As long as in the red cells there is 0, every of those features are disabled. Okay, so what we do is we save the sheet and we simply load it into NEUSREL and let NEUSREL run. And NEUSREL will write the results in here plus save all plots generated. Very important, close this file because otherwise NEUSREL cannot write into the sheet. So NEUSREL will give you an error message, can't write into Excel if you have this Excel open. Good. So, and now we arrive at number 3. There's a standalone version of NEUSREL and there are MATLAB-based version. I will now use simply the MATLAB-based version. So I have saved my file into desktop calculations, yeah, and I load this by typing x as load. I simply select tutorial case, and now this data is read by MATLAB. Once it's read, we can run NEUSREL by simply typing NEUSREL. NEUSREL. So now it's running. You see the first iteration. So it does 2 iterations, 3 iterations. And this may take now, I don't know, 5 minutes or so. So let me quickly go through 2 slides while NEUSREL is computing. So what NEUSREL will uncover are, for instance, those nonlinear plots. There are many types of nonlinearities. You could even draw a sinus curve there, which is a nonlinearity, or the most basic nonlinearities you see here, which is a progressive or J-curve, a hockey stick curve, digressive or saturation curve, a U or inverted U curve, or S-type curve. For instance, if you look at the saturation effect curve, it basically gives you the impact of customer satisfaction toward customer loyalty. If you would look at the first glance onto it, you would say, I don't know, it's kind of linear. But if you have a closer look, if you increase from 8 to 10, you maybe gain, I don't know, max one scale point in customer loyalty. That's increase. Now you already get here some results. But if you decrease by 2, you gain approximately 2, -2. Or even if you decrease from 6 to 4, that's even more obvious. It's more than 2. It's 2.5. So the impact which increasing satisfaction has is more than double as high when satisfaction is low compared to when satisfaction is high. So you see there's a strong difference between the impact depending on where you come from. That's why it's so useful and important to know that. These are the interaction effects we get out of NEUSREL. There are also many different effects which are possible. You can draw any kind of wave you like, basically. But the most fundamental things you will see are AND, so a conditional, which is in the middle. So basically an impact can only be achieved if you have both success factors at the same time given. The OR relationship on the right, which basically tells you that a success factor has only impact if another success factor is low. Either the one or the other, both together, is not very efficient. And the left is an exclusive OR that basically a certain success factor is positive when another is low, but negative if the other is high. These are the most fundamental interactions. And this is interesting to many people because when statisticians talk about interactions, they always think about product terms, which is nothing else than an AND combination of two factors. Okay, so here's some background on the causality testing methodology we are using. So we are not using the PC algorithm so far, simply because we found that they are not very helpful in larger models. So typically, holistic larger models, we see that a certain outcomes has many factors that drive that. In statistical terms, they are non-sparse. And PC algorithm is a methodology which works reliably only in sparse environment. So can you quickly explain the logic behind the PC algorithm? If you have the variable A and C correlating, as well as B and C correlating, and A and B are not correlated. If you know these three things, you can triangulate and conclude that the causal direction must be from A to C and B to C. Otherwise A and B must correlate. Right? That's the logic behind it. So you triangulate with conditional independence testing, and yeah, because of that, you build causal and learn causal directions. So this is a very powerful mechanism. However, it has a strong failure rate with non-sparse environments. So that's why we haven't implemented that in NEUSREL. Rather, we use lately discovered methodologies which read and test causal directions out of the residuals. So the basic logic behind that is that if we assume, again another assumption, but if we can assume that the residuals, the noise, is independent from the cause, then we can derive out of these residuals, we can derive whether or not here's a causal assumption. So if you look at those two plots, they are the same data, but inversely plotted. And if you do a linear regression, the red line from x to y, or from y to x, you will gain quite a different formulation, a different regression formula. However, the same explanation power. That's why you cannot read causality simply from the from regression approaches. However, if you look at the residuals, they look quite different. The first picture is evenly distributed, and the second picture is very unevenly distributed. So the assumption that the error is evenly distributed, which means basically it is independent from x, then x must be the reason for y, not the other way around. And this logic must be translated into the higher dimensional space, and this is what we have done in NEUSREL software. Okay, let's look into the calculation. So it already finished the calculations. However, it still writes data into the Excel sheet. Yeah, it has done the total effect calculations. You see already here some outcomes which you always already will find in the Excel sheet. Once it's ready, we will open the Excel and we'll have a closer look. But we can already start this with those pictures. What you see here are all different relationships, and you don't see a 3D plot. So that's why the threshold we put there was too high to gain any interactions. So obviously there's no strong interaction. When you look here, we see mainly two nonlinearities, these two. Yeah. Let's look into this one first. This is what you already know. This is the satisfaction driving loyalty. So again, it has a strong impact. From 3 to 5, it increases by 2.5, and from 8 to 10, it only increases by half a scale point. Yeah. You may ask, okay, why is it varying? So basically, the blue line is a polynomial plotted into the plot, yeah? And the y-axis is not loyalty, it is the cost change into loyalty when departing satisfaction from its mean. So you will always see that around the mean of satisfaction here, which is around 8. When it departs here, the mean is always at 0. Yeah? And if we depart from this mean, we get a decrease in loyalty. So this is a simulation result out of the model. And if it is varying around the blue line, this means there is some interaction involved with other variables. This is not noise. Noise is singled out here. This is because of the specific calculation formula. Of course, some variation could be due to variations in the model itself. As you know, networks give a little bit different results anytime. So that's why they may be there may be also some imperfections in modeling the interactions with just 250 data points. These imperfections may be expressed by interaction, which is maybe not caused by the interaction, but the imperfection of the modeling. Basically, the variation is, again, no noise. This is another nonlinearity. The impact is not very strong. Huh? We see basically that here's some minor linear relation from 6 to 10, but no independent relationship when value is low. Rather, there's a strong variation here, strong eventually interaction. So we see here that the red line is very close to the blue line. This is typically, you will see typically if the inference variable has little factors, explaining factors. So you see here value is all driven by quality and expectation, and even quality is just driven by one factor, so it has no variation anymore among the blue line because there cannot be any interaction. So this is a proof that this plot does not include noise. It simply includes the independent effect plus the variation is an interaction with other variables. Okay, now we see our cursor and the model has been computed. We can look into the results. So any file you see here was generated. So basically there is a EMF file, which is basically a picture, which you can use later on in PowerPoint or whatever. There's a MATLAB figure. This can be used to manipulate the data. So if we open that, okay, I can load this into MATLAB, for instance, and can manipulate that. But I'm now interested in looking into our Excel file, where we have all the tabs. We have defined the model, and now we look at the results. The first tab is some overall measures. So you see here the date, calculation time, number of cases, and this is the goodness of fit, which is basically a mean of R squares of the structure model and the R squares in the measurement model. So it hasn't advanced a lot in those three iterations. But this is not unusual in models with reflective measurement models. And here we see the R square of NEUSREL always compared to linear regression. Yeah, so you see that quality is basically linear, obviously. Value is also quite similarly explained, satisfaction as well, but loyalty as well as complaints, we see a strong improvement in explanation power due to NEUSREL. What we also have here is the R square, which a binary scoring model would have. So basically, if you take the variables for loyalty and weight them using the correlation, you get also a predictive power, which is lower than linear regression, obviously. And naive predictor is basically the mean of any factors. As you see, they are even less. So this is just for comparison between different methodologies. And we already can conclude that those items and those relationships are probably more linear, and here we have some nonlinearities or interactions. The tab latent. Latents give us information about the measurement models. The factor scores of any of the 7 quality items towards the quality latent variable. Factor scores is a correlation between them. The weight is the weight, actually, the weight which is used to calculate the item out of the latent variable. And we have some other measurements of the quality of those latent variables here, COMAS alpha and so forth. Okay, that's the latent tab, and now we look at the path tab. The path tab, we see all those KPIs which we use to judge about the importance, the independent importance of certain factors. So this is similar to the betas you might know from linear models, but we don't have a linear model anymore. We want to have a KPI which includes linear as well as nonlinear relationships. That's why we have the average simulated effect, which is basically the simulation of the effect when we change the cause. How much will the effect will change? Yeah. So you see here that basically loyalty is driven by satisfaction and a little bit by value and complaints. Okay, these are only the direct effects, and this here is the effect strength. Yeah. So satisfaction and complaints are most important variables here. Okay, sometimes it can happen that there is no average simulated effect but a high effect strength. And this can happen if the variable is simply doing an interaction, or if the variable has a U-shape relationship. Because if there's a U-shape, the average simulated effect is 0, because the effect is positive and negative. Okay, we also have the unstandardized effect. In this case, it's the same because the variables are all scaled the same. However, in general, this is standardized by the scale of the different variables. And this is unstandardized. So you can really know that increase in complaints by 1 scale point leads to an increase of loyalty by 0.17. And lastly, we have the total effects. Yeah. So if you look at loyalty, quality has no direct effect on loyalty. Instead, it drives value and it drives satisfaction. And this is why actually quality is the most important factor. Yeah, the most important factor, but has no direct impact on loyalty. But overall, it's the highest causal impact onto loyalty. Okay, what else? We have more tabs here, which you might not always need. There is the nonlinearity tab. I will go into this in the advanced module. There's a prediction tab, which gives you the prediction for every case onto every explained variable. So that's basically the outcome of the model, the values. We have also the latent values, which is either if it is a manifest variable, it's a manifest variable, but if it's basically a latent variable, it can be it is a result of the different manifest variables. So you have the values for the latent variables at hand as well. Then what we also have are interaction effects. This is a kind of an effect strength of interactions. So if we look here, we see that especially complaints, loyalty interacts with complaints onto loyalty. And you have the reverse by complaints and loyalties. It's the same. It's the same value. Yeah. So here's an interaction. We have put the threshold on 0.1. This is why we haven't seen a plot here. Yeah? So if we lower the threshold to 0.05, we would gain a 3D plot for this, this, and this. We would have gained 3 interaction plots. We have another tab here, which is ASI. This is the average simulated effect of the interaction. So if you basically increase both variables, what's the impact? You have the impact figures here. Okay, so that's it. There are more outcomes, more features more stuff, but basically this is not what you need for the first steps. So you're ready now to go and do your own analysis. Good luck.